This North Central SARE Energy Conservation webinar session is, as Scott mentioned, about energy conservation for livestock and poultry production. So we'll be talking about energy use and conservation related to swine and poultry and dairy ventilation. As Scott mentioned, my name is Kevin Janni. I am a professor at the University of Minnesota in the Department of Bioproducts and Biosystems Engineering. We are joined today by Larry Jacobson and Hongwei Shin. Larry Jacobson is a professor also here at the University of Minnesota in the same department, Bioproducts and Biosystems Engineering. Hongwei Shin is a professor at Iowa State University with appointments in the Agricultural and Biosystems Engineering Department and the Animal Science Department. What we're going to talk about today, I'm going to begin with an outline of some concepts relative to ventilation that Larry and Hongwei will build on in their presentations. And Larry will talk about the energy conservation in swine production, and Hongwei will talk about energy conservation for poultry production. And then I'll come back and talk about dairy ventilation and energy conservation there. Other topics related to dairy conservation will be covered in other webinars later in the series. And then at the end, we will have some time for questions. So to begin, the ventilation is a very important part of livestock and poultry production for maintaining the environment inside the building that the animals are housed in. And by ventilation, we mean exchange of air between inside and outside the building. There must be this air exchange, otherwise we don't consider it ventilation. And for ventilation and air exchange to occur, we need exits or outlets and for taking air out of the building, and we need a place for air to enter and have through inlets. And this can be done in multiple different ways. And then finally, we need to have something that causes the air to flow. In mechanically ventilated buildings, we have fans that will provide that air flow and air exchange. And in naturally ventilated buildings, we have wind and buoyancy that cause this airflow. Many livestock and poultry fans have mixing fans or cooling fans. And from our definition today, this does not provide ventilation, because this does not cause air exchange. It does cause mixing, and it creates a local air velocity, and it has a cooling effect in warm climates or climate conditions. We expect a lot of our ventilating systems. They need to provide this air exchange, bring in fresh air and oxygen for the animals, and then they remove moisture and heat and a number of air contaminants that are generated inside the building and then maintain air quality in there. The systems, which has gone a little bit beyond just ventilation, often includes heaters that add heat in cold climates and cold weather, and especially for young animals and poults. In the hot weather, we will use a ventilating system to cool, and we may include an evaporative cooling system. And we expect this system to operate year-round and maintain uniform conditions throughout the barn. Proper heater management and thermostatic settings are needed to make sure that all of this heating and cooling is done in an efficient manner. It's clear then that ventilation does impact the thermal comfort of the animals and poults and birds that are in the barn, and it impacts the temperature and the humidity and the air quality. But sometimes it's not so clear that it's impacted by the number, age, and species of animals, and our colleagues will talk about that along the way. And manure management and handling is an important part of our ventilating systems, or it impacts it, and the air quality that they have in there, as well as the ambient temperature. We need to move more air in hot weather and can get by with less in cold weather. In swine and poultry production, feed costs usually account for 60% or more of the total production costs. And Larry and Hongwei will make the point that ventilating systems need to be well managed to be energy efficient. and while also providing an environment where the animals can have very good feed efficiencies and rates of gain. So practices that conserve fossil fuels but reduce feed efficiency or rates of gain are not going to be acceptable by producers. So we need to avoid excessive ventilation, and we also need to avoid having too little ventilation, or we need to watch out for having the building at the wrong temperature, either too cold or too warm, and we need to avoid creating drafts with the system. Finally, I want to talk about this concept of ventilating, agricultural ventilating fan performance. This is the key part of working with a ventilating system. The fans are the heart of the system, and to help us understand their performance, we need to know this relation between the airflow rate and the static pressure that the fans are working against and providing that airflow. So static pressure indicates what the fan must overcome or work against while providing this airflow. And this information or fan performance is measured by conducting standardized tests. These tests measure the airflow at different static pressures, and for agricultural fans, the static pressures range from 0.05 to 0.3 inches of water. Now, the static pressure indicates, again, what the fan must work against while it's providing this airflow. And the most common static pressure measurement that we look at for mechanically ventilated buildings is between inside and outside. Now, there are other factors that will impact the pressure difference that the fan must work against. Wind blowing against the outside will reduce the airflow rate. And if we've got a building that has the too small inlets, that will increase the static pressure and reduce the airflow rate. But the static pressure can be measured with a manometer as shown here and used to keep track of how the system is performing in the field. In negative pressure ventilation systems, this is the commonly used for swine and poultry, is we have exhaust fans that are blowing air out of the building, and this is creating a slight vacuum inside the building, and this is part of that static pressure that the fan has to work against. With this vacuum, we draw in fresh air through the inlets into the room or building, and we can use this to distribute the fresh air throughout that whole building. For most ventilating systems, we like to be operating in the range of about 0.05 to 0.1 inches of water. Generally, we want to keep less than 0.12 inches of water. Another thing that's important in picking fans and working with fans is the ventilating fan efficiency. Now, this is the relationship between the airflow rate, again in cubic feet per minute, and the electrical energy that is used. As you would expect, we would like to have a very good or a high fan efficiency rating. The best laboratory at the University of Illinois is an independent lab that conducts agricultural fan tests and publishes the results. You can get a hard copy by going to the Midwest Plan Service at www.mwps.org, or you can go visit online at the website there for the best lab at the University of Illinois. To save energy, it's important to maintain our fans, and so some of the things to do there are clean dirty shutters and grills, replace and repair damaged shutters, and if you are going to be lubricating shutters, it is important to use graphite rather than an oil, because oil tends to collect oil or dirt, and that reduces the operation of the shutters again. You need to manage the inlets, and remember, if you have a system where you are using ceiling inlets and you're bringing the air through the attic, you need to have enough room to bring air into the attic space to bring that out. And again, many fans have belts, and if you have belts, they need to be tightened to maintain their performance. Fan performance can easily be reduced by 40 to 60% if they're not well maintained. And in these conditions, you've got the fan running, and it's using electricity, but the airflow rate is just a fraction of what you'd expect. So, and you end up running more fans than you need to do that. So these are some of the key ventilation concepts we want to get across here before we get started, and that's, there's air exchange between inside and outside. We need inlets, and we need outlets, and then we need a driving force that's going to cause this ventilation. You'll hear a little bit how the ventilation rates vary for the different animals and different ages, and it's important that we maintain the proper environment with plenty of ventilation to enhance feed efficiency and growth. And then we'll come back and talk about these relationships between airflow rate and static pressure and fan efficiency. With that brief introduction, I'd like to turn it over to Larry Jacobson. Larry?
Thanks, Kevin. All right. What I'm going to be talking about, as Kevin already introduced, is the energy conservation in swine buildings. I think the information that Kevin gave or alluded to is that a lot of the energy that's used in pig production is what might be termed indirect energy or feed energy. But I think today's topic is primarily the fossil fuel energy or direct energy. And in the case of pig production, that's primarily LP gas and some electricity. Anything as far as the cost of production, depending upon the phase of production, we're from maybe 2 to 5% of the cost of production is this fossil fuel energy, and a much larger percentage is, of course, feed energy. And I guess we may just say, why are we even talking about this since it's such a small percentage? Well, the truth is a lot of the way the pig industry is structured, we have a lot of contract growers, and they do not participate in the feed. The owner of the pigs purchase the feed. So really, this is the only thing a lot of contract growers can control is the fossil fuel energy by not using excessive amounts of LP gas or electricity. There are certainly incentives that they can do if they get good rates of gain and feed efficiency. But this also the fossil fuel energy does play a role here. I just listed here some annual energy usage that we pulled from some of our Southwest Minnesota data files. Bob Kaler, who works in Southwest Minnesota, now retired, but pulled some information from various years from a particular producer for 3 years, 2006 through 8, on the amount of electrical energy that producer used per pig produced, and LP gas gallons per pig produced. And as you can see, it varies. Obviously, the gas is probably going to vary a little bit more because that's a little more dependent upon weather conditions and the number of very cold days or et cetera, or when the animals were young versus the time of year. But you can get an idea of how much energy is being used. Electrical energy is a little more consistent. So let's talk about ways to control this, what this direct or fossil fuel energy costs, and I've kind of categorized these as follows. Certainly, controlling or reducing the ventilation rates, as Kevin has already introduced, is key. There's issues about fan efficiency that he also touched on. little bit of concerns about insulation and leaks in the buildings. Insulation plays a role, not as maybe the same role that a lot of people think as far as heat loss, but certainly important in livestock buildings. And then this idea of environmental control, controlling the ventilation, heating system, and making sure all of those work properly is very important, because if that is not controlled properly, we can waste quite a bit of energy in these systems. This just shows a very simple heat balance that we as engineers use to determine ventilation rates or the amount of heat losses and gains in buildings. And I just wanted to show this because we can see the size of the arrows here, in particular the heat loss from a building is kind of proportional to the percentage of heat that is lost in a building. And you can see the arrows going through the walls and through the ceiling are relatively small, the blue arrows that heat loss. The exhaust air is a very big arrow, and that's the that is the primary loss in a swine barn, is the ventilation air. So it's very important. If we look at our ventilation rates, and this is cubic feet of air per minute per pig, these are recommended in Midwest Plant Service or other sources, and these are determined by heat and moisture balance. But the minimum rate is very important that we don't move more air than that, because often if there's small animals over very cool temperatures outside or cold temperatures, we may have to then use excessive or supplemental heat to maintain temperatures. So that minimum rate is determined to control moisture, and that should be adhered to pretty closely, as close as possible. If you get much below that, you got air quality problems. But if you get above it, you'll have the air quality will be good, but you may use a little more energy than you need. Actually, Kevin did show essentially this slide before, but I think the review is good. 99% of the ventilation systems in pig units are what we call negative pressure ventilation systems, where we have exhaust fans that are exhausting air from the building, creating this vacuum or static pressure. And then air enters the barn through design inlets. The static pressure that we're talking about is our target is about 0.05 inches of water gauge. We don't want to get much above this 0.12, otherwise the fans are going to have to work too hard. The airflow rate is reduced. It's measured with a manometer. This is the kind of simplistic system. There are some electronic versions of this, but this is a very important tool to use in managing ventilation systems and check this at certain times of the year. If in mechanical ventilation systems, then for swine barns, we really have three components of the system: the exhaust fans, the inlets, and controls, and this may be integrated also with heating, ventilating, and air conditioning system. There may be some preheated hallways in like a nursery building or farrowing, and in some particular cases for sows, there may be some adaptive cooling systems used. We do need to carefully select fans that are rated, and again, Kevin touched on this. This is the test data for a given fan, and it shows different static pressure starting at 0 up to 0.2 inches, and the airflow rate, CFM. As you can see, the static pressure goes up, that airflow goes down. Way over on the right side, there is this efficiency rating as well, CFM per watt. That is, again, an assessment of how energy efficient, how much airflow is produced by the fan at that static pressure, against how much energy is inputted into the motor. So you can see certainly as the static pressure goes up, our efficiency goes down. So not a good idea to operate too high a static pressure, even from an energy standpoint. There's other things that are not as good about that either. So our target is again between 0.05 and 0.1. And again, all of this information can be found in the BEST Ventilation Lab Handbook, either a hard copy or you can see this online at the indicated address here. If you do look at the BEST Lab, they will publish most of the fans that are used in ventilation systems, and they're usually categorized by the diameter of the blades, and I just pulled out 4 different fans from the BEST Lab, and you can see there's quite a bit of difference between these 4 fans. Certainly in airflow rate, and this is airflow rate at the same static pressure, or this 0.1 inch of water gauge. Everything from fan 1 low of 7,000 down to 4,000 for fan 4. And you can see the efficiency on the right varies a lot as well. So certainly when we select fans, airflow is very important. We need to select for getting the right airflow, but also you want to look at the efficiency. So you can see fans 1 and 2 have very similar airflow rates, and but there is some differences in efficiency. Fan 2 is quite a bit more efficient, has a higher CFM per watt rating. Okay, large fans, belt-driven fans, are also used a lot in livestock barns. Shown here, they're the primary fan used in tunnel ventilation systems. There is some issues about belt-driven fans that can be a problem, and that's making sure the belt is adjusted or tightened. We did some work quite a number of years ago, a little over 10 years ago, where we were measuring airflow rates from these large fans, and the blue, the BEST Lab number is up above there. That's what the BEST Lab says this fan was capable of moving, so over right around 20,000 CFM at the operating range. In this particular case, it's pascals. 30 pascals is about the 10th of an inch. The fans that we were measuring, for whatever reasons, had belt slippage, and the red or pink line is actually the numbers, data that we recorded, and so the fan was moving probably half of the airflow rate that the BEST Lab said. It says it was capable of. After making the belt adjustment, we got the airflow rate up where the blue points are, blue line. So we increased the airflow rate considerably by having the belt properly adjusted. So you want to make sure that belts are tight on these large belt-driven fans. Dirty fan shutters can certainly reduce airflow rate and reduce efficiency. As much as 40% reduction in the airflow rate. That was some work that was done here in Minnesota a number of years, quite a few years ago. And it's just as simple as making sure the shutters are operating right and lubricated properly. This slide talks about some attachments to exhaust fans that are a little surprising. If you go to Best Lab, the shutter and guard only on a fan would be the red line. That would be the rating, the airflow rate, airflow on the vertical column versus static pressure on the horizontal. If you put a wind hood on it where the air has to move 90%, your flow rate or your fan capacity or ratings would be the blue squares. It would be reduced about 10% or 10 or 15%. If those same fans had discharge cones on, like you see on the right, the actual airflow rate is increased. It would be the green triangles. So you can actually increase the airflow rate of these exhaust fans. Most of the time these are 24-inch, 36 or 48 or 50-inch fans. By having discharge cones, they will increase and make the fan actually a little more efficient. So that's certainly something you want to be aware of. Also, you want to make sure if you have those cones, they are maintained and kept in place. In this particular case, the fan lost that capability, and we really don't know what the performance of that fan is that had most of its discharge cone moved. Finally, I think Kevin did mention that when we're talking about what the fan has to work, again, the static pressure, the wind forces that are blowing against the fan from the outside actually create a static pressure as well. And in some particular cases, like on the end of a barn that has all tunnel exhaust fans, some windbreak fence, like shown here, can be helpful in trying to kind of reduce that effect under those certain weather conditions. Okay, let's talk a little bit about insulation and the insulation in barns are primarily used in livestock buildings and pig barns specifically to keep our surfaces dry. Many times in finishing barns, we have a 6-inch knee wall of concrete that may not even be insulated, and if you have 70 degrees inside and it's 0 degrees Fahrenheit outside, that inside surface temperature is going to be at the low 30 degree Fahrenheit level, and most of the time you will get condensation on that surface, on an uninsulated surface like that, and the heat flow indicated by the arrow there at the bottom. It will also be a fair amount of heat that's lost. If you insulate that knee wall, say with about an inch and a half of foam insulation, and get the R value up to around 6, under the same conditions, the surface temperatures increase very significantly, and you prevent, for the most part, condensation unless you have really humid conditions inside, and of course the heat flow is reduced too. So insulating livestock buildings is really the first primary need for that, is to prevent condensation or keep our surfaces dry, but it certainly also will reduce heat flow and save us some energy. A little bit on curtain management. A lot of our pig barns, even if they are mechanically ventilated like the tunnel barn, will often have a end wall curtain, or certainly the curtain-sided barns that are essentially mechanically ventilated during the wintertime in the Midwest, but are naturally ventilated in the summertime. It is important to make sure that we don't have a lot of leaks in these curtains, or they're tight, because leakage can really increase the air exchange in the barn, or uncontrolled air exchange that subsequently can cool off, and we have to make up that heat with heaters. Here's sealing the end wall of a tunnel ventilated barn is oftentimes a good idea in the wintertime if that end wall curtain is not going to be used at that time, or the use of this bubble wrap insulation for winter on the inside can really can be effective to not only seal up the curtain but also provide a little bit more insulation and keep that surface from getting wet again. Similar conditions to what we talked about with the concrete wall. Let's talk a little bit about controllers and the interrelationships of heaters and the fans. Most of the modern pig facilities have the ventilation system and heaters are controlled by a central solid-state controller. Controller set points are very important. We don't want to get those too high, otherwise we can actually use excess energy because we're going to be maybe using more fuel, LP gas, if it's set too high for the size of pig, or if it's set lower, we can actually use we'll use more electrical energy because there will be more fans running. So again, there's a compromise. This is pretty sensitive to temperature. Even a few degrees can make this swing quite dramatic, as these projections here show. Probably the most important thing is the heater and the relationship between the heater in the barn. If you have an LP gas heater, you see these are direct fired heaters, and the relationship between that heater set point and the fan that controls the temperature, often called stage 2 exhaust fan. They really shouldn't overlap. The heater offset, if it's set too tight, may overshoot and turn on these temperature control fans, and you'll get a cycle going, and you can really use a lot of heat. Also, the probe location for the controller, you want that in a location that's not too close to a heater or to an inlet. You want that to represent the temperature. So that's pretty important. Most of the time there'll be a couple sensors in these larger rooms. And then the last point there, really you got to be careful about oversized or excess heaters, and that's a pretty common situation. As a suggestion, we usually say to have a heater offset at least 1.5 degrees from the set point to prevent this heater overshoot. Most of the time that will then allow enough time so for once the heater is shut off that the temperature in the barn doesn't continue to rise and turn on the temperature controlled fans. There's generally in pig facilities pretty much accepted that most of the heaters are oversized. Most of the direct-fired heaters have probably a capacity of like 250,000 BTU per hour units. You can buy heaters down to 60,000 BTU heaters, but the difference in price is usually pretty small. So most producers end up getting these large heaters thinking that, only another $100 I can get and double my capacity. Actually, most of these heaters now have a valve that you can close off, this blue valve that actually reduces the output of the heater by about 65%. So instead of 250,000 BTU output for a hanging heater, if you reduce that valve, it'll be more like about 150,000. And I know a lot of producers that essentially turn that valve down and operate the full year at that reduced rate, and they save energy. They also, by that way, kind of prevent this overshoot from occurring as well. Okay, I really haven't talked much about the indirect energy costs, and that's really probably topic for another session, but certainly it's very important from a pig performance to have a good environment. It'll impact the performance. Feed efficiencies are very important. Even a small change in feed efficiency can be amount to a big amount in feed usage and energy savings, and that kind of subsequently will save, of course, energy on less crops and energy used to produce that feed. Also manure handling. If less manure is produced or water means there's less energy needed to apply the manure or pumping and all of those things. And there's certainly issues around the building materials that we are starting to get into or concerned about when we start talking about footprint and energy input or the environmental input of footprint of these buildings. So I think with that, I will turn it over to Hongwei, and Dr. Sheen will talk about poultry energy usage. So, Hongwei.
All right. Well, thank you very much, Larry, for the introduction. I have the slides, please. Okay. Great. Well, yes, indeed, I'll be talking about energy conservation for poultry production. Kevin and Larry have laid a solid foundation about some of the general concepts and the good applications, so I'm going to talk a little bit more about the poultry aspect. Basically, I wanted to approach this from two angles. Once again, looking at maximizing feed energy efficiency, therefore cash return through best management practices, sort of the indirect energy conservation, and then talk about the optimizing operation of the heating ventilation systems to increase the energy efficiency directly. This chart actually shows the partitioning of egg production costs through our recent survey of the Midwest egg industry. Once again, kind of a mirror of what Larry has indicated. The majority of the production cost is really from the feed energy. In this case, we're looking at 64%. And the utilities, as the purple slice of pie indicates, is 6.7%. And so therefore, any management that leads to increase the feed efficiency will definitely have a positive impact on our profitability of the bottom line of the operation. So to start with, I'm going to talk about the litter and manure management. We have demonstrated repeatedly that fresh bedding would significantly reduce the minimum ventilation requirement for indoor air quality, particularly for ammonia control in the case of poultry. And that will lead to reduce the energy use and ammonia emission. It will likely improve the animal performance for meat birds, the body weight gain, livability, condemnation at the processing plant, and the feed conversion. And it is a common practice that people remove the cake, the litter between flocks. This is for broilers and turkeys. And also, more and more people start applying ammonia control chemicals on the built-up litter. This just demonstrates the minimum ventilation requirement for ammonia control to keep it at 25 to 30 ppm in the broiler house with built-up litter versus the new litter. The light blue line is the reused litter or the built-up litter you can see during the 10-day brooding period, and how much more ventilation is required for us to achieve the target ammonia concentration of 25 to 30 ppm. So it's as high as 9 to 10 times at the beginning, And this, of course, corresponds to the time when the most heating is needed. So as compared to the new bedding or the Midwest Plant Service recommended minimum ventilation. So just how much extra LP gas used then for ammonia control as a result of the extra ventilation. Say for a broiler barn of 40 by 500 feet with 24,000 birds, and it really depends on the outside temperature during that 10-day period of time. So in this case, if we look at outside temperature vary from positive 10 degrees to minus 25 degrees, and the extra LP used for the first 10 days vary from a little over 600 gallons to a little over 900 gallons. And depending on the price, of course, it costs anywhere between $1,000 to $2,300 of extra fuel costs. I think in the Midwest right now, depending on whether you have locked in the rate, these days, sort of typical LP is at $1.75 per gallon, and but as the price go up, so that could become quite substantial. So in the Midwest or throughout the country, actually, bedding availability is an issue, and of course the cost. So this just show what if we replace the bedding, the litter every flock for a 40 by 500 barn, 20,000 square feet floor, and to do a house with a new bedding would take about 24 tons of new bedding. Okay, oat hulls or rice hulls or shavings. In this case, I think the prevailing rate is about $70 per ton of a bedding. So it'll take about $1,680 of worth of bedding to cover the area. And so that, in addition of saving of the LP gas, which vary from $1,100 to $2,300, if we assume the feeder conversion is improved from 2 to 1.96, or the industry folks will refer to as an improvement of 4 points at a market weight of 6 pounds per bird for broilers, and a 95 livability, the feed savings itself would be estimated like $1,600. So it's basically enough to offset the extra cost of the bedding. So the potential benefit is there. And as indicated, the impact of new bedding versus build-up litter on ammonia, you can see the new bedding would lead to reduced ammonia emission. This is throughout the flock of broilers. Our recent research indicates that. The vertical axis is the cumulative ammonia emission per bird, and depending on the market age of the birds, anywhere between 20 to 30% of reduction in terms of total ammonia emission from the barn with different sort of bedding. And this one here demonstrates how often you move the manure out of the barn. This will be more applicable to laying hens, and how that impact ammonia emission generation in the barn. So if you leave the manure on the belt for 1 day versus 7 days, you can see the drastic differences. So these days, the industry people pretty much use daily manure removal or every 3 days. And the data here certainly show that it will reduce your minimum ventilation requirement. Manure belt houses for layers are getting more and more popular. The majority of these houses built today are in the form of manure belt versus high-rise. And these manure belt houses, typically they use some sort of manure drying mechanism. So in this case, the one to the right, the forced air blowers, is fairly typical, where they recirculate the internal air and over the manure belt to dry the manure, and so that the manure will be easier to handle for transportation and storage. The one on the left side is used to exhaust air, basically use the residual heat to dry the manure. So obviously that one, the left one, save energy, but you do need to have an additional drying chamber. Topical application with chemical additives, again for meat birds, this is typical. And the idea is trying to suppress ammonia emission during the brooding period of time. And as the chart shows to the right, the blue lines, for example, use of alum to suppress ammonia is fairly efficient, especially in the early stage of the brooding period. And some people use a little bit higher dosage, trying to keep that efficacy a little bit longer. So this really boils down to reduction of minimum ventilation. Okay, so heating systems obviously is a very important part of this, and here's just a few things that producers probably should ask themselves. When was the last time the control temperature sensor checked or calibrated? I think Larry touched on this already. And the false readings obviously will lead to adverse effect on the bird performance and energy efficiency. The other thing we look at, even though the thermostat and temperature sensor are perfectly accurate, but if they are not placed at the right location, especially measuring what the animals are experiencing, that really doesn't do the justice. So, for example, for broiler chicks, day-old chicks, if you measure, say, 4 feet above the floor, the birds is at 2 to 3 inches from the floor, then you have to really consider if the temperature measure indicative of what the bird's comfortable level is. Okay, so the uniformity, Kevin already talked about that, and just because people say, well, I get a good mean temperature throughout the barn, no, that's not quite enough. Use layer as example. If average, they take about 100 grams of feed, but if the barn vary from one end to the other end due to temperature stratification, the feed intakes, they vary from 90 to 110 grams per bird, and you're going to have a lot of variability on the egg size, which is not desirable. This is shows things, how things should not be done, in my opinion. I think we touched on that a little bit too. So you can see the heater placed next to exhaust fan, and it is a challenge in some of the cases where you have large barn and trying to have a few space heaters, trying to how to distribute that heat evenly. So there are some things that needs to be done yet for us to really to more efficiently utilize the heater in this case. And we need to look at the replacement of old brooders with new energy efficient brooders. And this chart borrowed from Mike Zarek at the University of Georgia, and he done some action measurement of thermal imaging, looking at the temperature distribution of conventional pancake brooders versus reading brooders. You can see the coverage area for the modern reading brooder is easily twice as big, and so this is something that the producers should be looking into when they look at the renovation or improving their heating systems. And just looking at this particular slide, you can see the hulling of the chicks as indicated by the yellow color. That's the indicative of lack of number of heaters in here. So once again, you burn LP, but not doing the job properly. So make sure you have sufficient heating capacity in the barn. All right, moving on to ventilation systems. So first, we got to make sure we have enough ventilation capacity to cover a year-round requirement. And secondly, once we have that, how do we efficiently use our resources? And obviously, we need to have proper air change to avoid condensation in winter. Larry touched on the proper insulation is important, but also once you have that, you still got to have an adequate amount to move that moisture out of the barn. And last winter, we have quite a bit of folks that are experiencing some condensation issues, and which is caused by lack of minimum ventilation. Maximum cooling effect in summer is equally important, and cannot emphasize enough about the importance of maintaining proper static pressure, uniform distribution of the air, okay, and a good management decision. Use of nocturnal cooling, for example, one of the things that could probably potentially reduce some of the peak load demand by further cooling at night. This is just recommended ventilation rate for poultry. The rule of thumb is that the mild weather is about 5-6 times the cold weather minimum ventilation. The hot weather is about 10 to 15 times. Okay, so you can read about this at your leisure time as reference. Just a review of the airflow pattern in animal house. Kevin already touched on this. Cross ventilation and tunnel ventilation. Okay, and an application of tunnel ventilation in the broiler barn. The idea is basically to increase the cooling effect by helping birds lose body heat faster. Here's an example illustrating the differences between cross and tunnel ventilation in terms of air velocity. So we have broiler barn 40 by 400 with 10-foot ceiling and ventilated at 100,000 CFM airflow. So calculate the air velocity is the flow rate divided by the area, cross-section area. Okay. So cross ventilation, the area is 4,000 square feet, and we have average air velocity of 25 feet per minute. Whereas you have tunnel ventilation, you'll be looking at cross-section area of 400, and then the air velocity 250 feet per minute. So 10 times as great as large. And so this shows the relationship between the effective temperature and air velocity for poultry. Effective temperature basically is the temperature being felt by the animals. So the air temperature in this case, for example, is 90 degrees. But if we have a air velocity of 250 feet, the bird actually feels the air is like 78 degrees. So we're adding some wind chill effect to the birds in the summertime. So that's basically the idea of tunnel ventilation. Whenever the conditions permit, we should consider natural ventilation to save energy. And a lot of time, we achieve better indoor air quality. It really doesn't take a whole lot of wind if it comes in the right direction to achieve the barn's air change need. And the graph shows air change per hour versus the wind speed, and at a curtain opening of 1, 2, or 4 foot. Okay, so as you can see, if we use the threshold of 60 air change per hour or 1 air change per minute throughout the barn, and it really only takes about 2 miles an hour for a southeast wind or a southwest wind for a east-west oriented barn to achieve that air change. It was a 4-foot opening, only 2 foot, 2 mile per hour, and so on and so forth. So again, on a good day, windy day, so it doesn't need to be too windy to achieve the good natural ventilation. String fans or cooling fans, I kind of sort of talk about this. Turkey folks, pretty much they use a lot of the string fans in the Midwest. And in a recent study, we actually converted barn into a tunnel fan. The data is somewhat anecdotal, but according to the producer, the tunnel fans are really more efficient in cooling the birds and creating more uniform air throughout the barn. And his record indicated the bird did have improved weight gain and feed efficiency. As a result, he has decided to convert all his barns from the natural ventilation or string fan into a tunnel fan. Okay, so want to again revisit the fan efficiency versus static pressure. Okay, so in this case, you can see, let's say 48-inch fans. We're looking at 2 static pressures of, we're looking at a 0.08 static pressure or the 0.2. Okay, so look at the fan efficiency. All right, keep that in mind. And if we have layer barn with 80 48-inch fans, 1 horsepower running continuously, the difference in fan efficiency is 18.5 versus 12.3 CFM per watt. Okay, so in other words, the fans running at 0.2 static pressure is 66% as efficient as running at 0.08. Okay, so if running all 80 fans use 1,400 kilowatt-hour electricity per day, or about $100 at the 7 cents per kilowatt-hour. If we want to achieve the same ventilation rate at 0.2, we only need to run 2/3 of the fans needed if those fans running at 0.08. So the electricity savings for, say, 3-month period, we're looking at about the $3,000, okay? And also the reduced static pressure that the fan works against will also lead to the increased lifespan of the fan motor. Okay. In summary, energy efficiency, conservation, and high profitability can be indirectly achieved by exercising BMPs, and energy conservation can be directly achieved by properly designing and operating animal heating and ventilation systems. And just few specific energy conservation means, including reducing ammonia generation in the barn and the ventilation and heating needs in wintertime, use and properly place energy efficient heaters and increase cooling efficacy through tunnel ventilation, avoid excess building static pressure, I cannot emphasize that enough, and also use natural ventilation when conditions permit. That concludes my presentation, and now I'd like to introduce to you Dr. Kevin Janni, who will talk about energy conservation for dairy ventilation. Kevin?
Thank you, Hongwei. Had to kick the mute button there. Again, my name is Kevin Janni, and I'm going to talk a little bit about dairy ventilation and some of the elements there and where we can do some conserving. Here is a little summary from a report on energy audits in New York from about 30-plus operations of both the freestall and stall barns, looking at the electrical energy use. And off to the left here, the red piece is the energy relative to ventilation is about 22%. And again, other people in the later webinars will be talking about other energy conservation methods. So I'm going to just focus in on dairy ventilation systems. And as you see in the other species, we in dairy also use natural ventilation and mechanical ventilation systems. And in the natural ventilation, we have barns that have mixing fans, and we have barns that do not have mixing fans to provide this air mixing and draft effect across the animals, as Hongwei talked about, relative to even the poultry. In mechanical systems, we have exhaust barns, exhaust fans with inlets distributed around in stall barns, and then we have now more tunnel ventilation and cross-ventilated barns that we're seeing out there. And we'll take a little look at some of these different things as we go forward. Okay, natural ventilation. Again, the driving force is wind and buoyancy, and so we have large sidewall openings that can be closed up in the wintertime to provide a windbreak, and in the summertime they catch the summer winds, and we have an open ridge so we can have air blowing in one side and out the other, and some going out of the ridge. With natural ventilation, we need to avoid obstructions, and those obstructions can be other naturally ventilated buildings nearby, the milking center, trees, any other kinds of things like this, and we need to avoid that to use that wind as effectively as we can. And we've seen now over the years that more naturally ventilated barns have put in mixing fans, and we see two kinds of things. We see axial fans that are hung in the area and blow down towards the animals in the pack, or well, in the compost barn on the pack, and in the stalls. And then we have high-volume, low-speed fans that are very large diameter fans that provide mixing. These axial fans typically are 36 to 48-inch diameters. They can be either direct or belt-driven fans. And you'll have multiple fans. The throw is usually 10 times the diameter in feet, so 30 feet is how far apart with a 3-foot diameter fan. 40 feet apart with 4-foot diameter fans is typical. And they can be combined with some sprinkling watering system to provide some extra cooling, and then they do the mixing. Key thing is to mount them so that they blow down towards the to the cows. A colleague a number of years visited the barn and was checking on the mixing fan performance and observed that they were mounted too vertically, and so it was just mixing the air above and not getting down at the cow level. So it's important to mount them with a bit of an angle so that they blow downwards towards that. These high-volume, low-speed fans, again, come in a range of sizes. The diameter of the blades can be 8 to 24 feet in diameter. They operate at a comparatively low revolutions per minute, and the velocities that you get off of that is much lower, but they move a large volume of air. So it doesn't take very many fans and very much horsepower to provide mixing in a naturally ventilated barn, again, whether it's freestall or compost. I borrowed this picture from Hongwei's presentation. Again, in the mechanically ventilated barns that I want to talk about are tunnel ventilated barns, where you bring the air in on one end, down the other side, and out with fans on the other far end. And now we're seeing cross-ventilated barns in dairy, and they are laid out a little differently and have air coming in on one side and out the other side on the fans. In tunnel-ventilated barns, they can be stall barns or freestall barns, and they can be modified or built new with this. This is a picture of a freestall barn with tunnel ventilation, and during the cold and mild weather, it just uses natural ventilation, and the curtains are opened up. And when it gets really warm, the curtains will go down on the sides. The door on the end with the fans here that's showing, that door would be closed, and the other end is kept open, and those 10 fans become blowing out, and that barn then becomes a tunnel with fresh air coming in on one end and blowing out the other end as part of the tunnel ventilation system. Cross-ventilated barns are laid out a little differently. They are taking, these are totally mechanically ventilated barns. They may have as many as 6, 8, 10 or more rows of free stalls and multiple feed alleys in there, and air enters from one side to the other. In this picture, the air would come in on the right and flow towards the left where the fans are. And these barns, cross-ventilated barns in the dairy, have these baffles, which we have here. Here in this area here is a baffle that's hanging down over the free stalls, and this drives the air down into the to the freestall areas so that air doesn't just flow over the top and does not provide as much cooling there. And so one of the things that's with these is that these baffles. Now these baffles do contribute to the static pressure drop, but they are managed. This is a cross-ventilated barn. The top picture shows the exhaust fans blowing out one side. They essentially have fans side by side the whole length of the barn. And then the other side of the barn has an evaporative cooling pad that serves as the inlet. And again, they may have 10, 12 rows of free stalls in there, and so this needs to provide the ventilation year-round through there. And it is all mechanically ventilated. The building is way too wide for natural ventilation. I also want to again hit this business about the fan testing data and fan performance here. This is similar data that Larry showed for a 24-inch. This one is for a 48-inch diameter fan. And as you can see it here for the different static pressures, we see the speed, the RPM doesn't change very much, but the airflow rate, again, decreases as that static pressure goes up and the efficiency goes down. Now, if you compare these efficiency numbers to the fan that Larry showed, the 24-inch, these numbers are much better. So it's common or larger, that the larger diameter fans have greater efficiency. So it's not a good idea, though, to put in too big of a fan, because then you'll move more air and not do the job that you may want to do it. Again, the same point that Larry had, I want to hit again, is that the same diameter is not the same airflow rate. So we've got 3 fans here. The first fan is the one that was in the previous slide, and it moves 19,300 CFM at a tenth of an inch of static pressure and has an efficiency of 20.1 CFM per watt. Another 48-inch fan moves 18,500 CFM, but its efficiency is down to 14.8. So if we have a third fan, moves more air, but the efficiency is down less than fan 1. So if we replace that first fan with any of these other fans, we're going to get a different flow rate and a different efficiency. I also want to hit the point that Hongwei had about the electrical costs per fan, because with these tunnel ventilated barns and these cross ventilated barns, we have a lot of fans. Tunnel ventilated barns, depending on size, can be 4 to 40 fans on the end, and freestall the cross ventilated barns 40 to 90 fans in the 48 to 52 inch range there. So here's 2 fans, 48-inch diameters, tenth of an inch of static pressure, so actually on the high end of it. And if we're running it for 24/7 for 120 days or 2,880 hours, the more efficient fan, number 1, saves us $84 per these 120 days. If we have to move 5,000 CFM, we need 26 of those fan 1s to do the job, and we'd need 27 of fan 2 because it doesn't have the same capacity. And we can save there $2,500 in this 120 days. Now, if we do the same thing again that Hongwei talked about, as we increase the static pressure, here we increase the static pressure. That's going to lower the flow rate, and it's going to lower the fan efficiency. Comparing fan 1 and fan 2, I'm going to spend about the $87 less with fan 1 in 120 days. And when I need to move the 5,000 CFM at this higher static pressure, I now need to run 28 fans at with fan 1 and 30 fans with fan 2. About 2 to 3 more fans are running, and it's going to cost me with the fan 1 about $2,000, almost $3,000 more. So again, we need to make the point that energy efficient fans, especially as we're using these large fans, is very important on energy costs, and getting the static pressure down at the range where we need to have is very important. And so what are some of these airflow restrictions that can be an issue? Well, one is insufficient inlets areas, because we increase the velocity and that increases the static pressure. Here are some guidelines for inlets for tunnel ventilated barns is given here. And here's a picture of an evaporative cooling pad that's accumulated some dirt, and so that's going to restrict the airflow that's going through there, and it's not surprising. It picks up dirt. It's always got air blowing in. And again, Larry mentioned this too: dirty fans, corroded fans, broken shutters, slipping belts, and these kinds of things can really restrict your airflow rate. So while there's a whole number of energy topics at dairies and ventilations, about 22% of it, subsequent webinars are going to cover some of these topics a little bit more. And so with that, ends our presentations on energy conservation for livestock and poultry. I want to thank my colleagues, and I will turn it back to Scott.